Okay, great. So hi, everyone. I'm Dylan, and I'm going to present some research that I've done in the past few months. So before I get started, just a special shout out to Chris Brown. This project wouldn't be possible without his help collecting the data from one of the virtual competitions. So huge thanks to Chris. So I'd like to talk to you all about transformers, jump rope, and the current state of the art of machine learning. So to make that actually make sense, I'll first go over my motivations for this project, and then I'll introduce some of the machine learning background that will hopefully help you understand why this model can do what it does. And then I have some really cool demos on some real speed videos from a real competition. And then I have some future ideas for where this project can go. So just some quick context about me, about jump rope history, and about my research. So I started jumping back in 2004. So to put that into historical jump rope context in terms of speed, I looked at the results from the 06 FISAC championships, and the world record, or the world champion 30-second speed score was in the 80s. Compare that to Norway, where it was 108. There's been a clear increase in the speediness of jumpers in the past decade or so. And then right now I am a PhD student at Case Western studying machine learning. So specifically, I try to learn useful representations of biological data. So I won't go into too much details, but this is just an example of some of my current research, where every one of these points represents a cell, and we have data about the 3D structure of that cell's DNA, and we want to separate those cells and distinguish the different types. So all of these are different cell types from the prefrontal cortex. And so if you compare my approach to one of the most used current approaches, you can see I separate out some of these self-similar cell types. So by learning useful representations, you can do some really powerful analysis. And that's hopefully where I can apply this to speed. And so my main motivation behind this project is that jumpers are getting incredibly fast. So right now, the world record holders are up to nearly 4 right-footed jumps every single second in 30-second speed, which is really ridiculous. And real-time human scoring is becoming infeasible at those speeds. Even at lower speeds, human error is pretty much guaranteed. So these are some data points from the at-home opener. And so there were 3 judges for every single event. And so you would expect the judges' scores to be perfectly correlated, but you can see that there's some errors even when scoring speed from video. And besides that, in real competitions, you're going to have jumpers that are incredibly fast that this error is just going to grow. And also competitions are growing in numbers. And so we would increasingly need more and more and more accurate judges to be able to run these competitions. And so hopefully that's where some of my research could come in. So very broadly, I work in a subfield of machine learning called representation learning. And so the main goal of representation learning is you have some very high dimensional data, maybe a bunch of images of faces, where every image is maybe 1 million pixels. So you have 1 million dimensions to your data. And we want to compress every single one of those data points into some low dimensional feature space that describes that data very well. So you could imagine if we have a bunch of images of faces, some meaningful low dimensional features of those faces could be the hair, the emotion, or the face rotation. And so rather than describing an image in terms of 1 million pixels, we could describe an image in terms of maybe just 100 or so of these high level features. And so most of the current approaches to do this involve convolutional neural networks and these generative models where you can actually generate new data that's never been seen before. So that's what's being done here on the left is we have, those high level features, and we just generate a bunch of random ones, and then we see what comes out. So all of these faces don't exist. None of these people are real. And if you want to play around with this, you can actually go to this website, thispersondoesnotexist.com, and it will generate a new one of these every time you load it up. So it's really fascinating how far this has come in images, but generalizing to video is quite difficult. So my first attempt at solving the speed counting problem I did for a final project in one of my computational perception courses. And so I just manually made a very limited data set from some videos I found online, and I trained it on my poor laptop. So I just trained a simple CNN classifier to try to detect when a jump occurs in a sequence of frames. And it definitely learned something. So here's a model I trained on the motion of the video, and here's one I trained on grayscale videos. So you could maybe make the case that this is representing maybe feet moving up and down. But in the end, it didn't really work that well. And so the reason for that, I think, is because of the limited data and computing power, but also because continuous video is very hard to process. The reason for that is that images have very clear spatial dependencies. So a pixel in this corner is probably not going to be dependent on a pixel in this bottom corner. So we only look at a very small local neighborhood of pixels. But in video, you can have really complicated time dependencies that are really hard to learn representations of. And so that's where transformers come in. So the main idea behind transformers is you want to train a model to recognize what it should pay attention to, and it's going to change its behavior based on what it's paying attention to. So this was proposed for natural language processing. And the way we do natural language processing for computers is we convert every word into a token, and then we process each of those tokens one by one. So you could imagine processing this sentence. It is in this spirit that a majority of American governments have passed new laws since 2009, making the registration or voting process more difficult. So now if you trained a transformer model on natural language and you fed it this sentence, when it is processing the token for making, it is paying attention to these two words up ahead more difficult to form the complex dependencies that make up the phrase making more difficult. And so it learned this just by looking at a bunch of examples of natural language and learning those dependencies. And so transformers are able to learn very, very general dependencies in any kind of data. And so this is a picture you could keep in mind if you want to think of transformers in terms of maybe some terms you're familiar with. So neural networks are really all the buzz in machine learning. Convolutional neural networks are a specific type of neural networks that work really well in images. Transformers are sort of more general than neural networks. So every neural network could be represented by a transformer, but there's transformers that no neural network could represent. So they're, in a sense, more powerful than neural networks. And so that's where we can finally apply all of these concepts to counting speed videos. So I won't go into the details of exactly how this model works, but essentially they learn two representations. They learn a representation for every frame. And so that's using known concepts, just convolutional neural networks to compress those images into meaningful features. But then they feed all of those representations into a transformer model that learns a representation of the entire video. And so by doing this, they can learn some really complex time dependencies that represent periodic motion. And interestingly, they actually trained this entire model on a automatically generated data set. They would scrape videos from YouTube and then just play them forward and backward a bunch of times to generate fake periodic motion. And so this whole model can be thought of as a single function that is end-to-end differentiable, and then you can just train it using some sort of stochastic gradient descent method. So that's when we have some demos to get into. So I applied this model to some videos from the at-home opener, as well as some videos of my own, and it seems to work reasonably well. So this is an example of it running on a video where the jumper is not even fully in the frame and the camera is not stationary. So one of the main, I guess, appeals of this model is that it's meant to work in any video in the wild. So in the wild just means you pick any video from the internet. If there's periodic motion, it can detect it. And so in a competition setting like this, where jumpers were just recording their own videos, it's not very controlled. And so this is the perfect opportunity to test out a model like this. So we were within one of the combined score of the 3 human judges, which is pretty good. Another cool thing about this model is that because it's trained to generally detect periodic motion, it can also detect when that periodic motion stops in the case of a mistake. So I'll skip ahead a bit to when the mistake happens. You can see the periodic prediction drop as the mistake happens, and then it will pick back up when the jumper resumes and the count will continue. So I think that's pretty cool. It does seem like we maybe missed a few jumps in between, or maybe there's some other parts of the video where it's less confident and it can't actually make an accurate prediction. So we weren't quite within the exact true count from this video. To actually put some numbers to this, I had 43 videos from that home opener that had accurate human scores from the judges. Out of those, the model scored 24 of them as high confidence. So it basically outputs the count and a probability measure saying how confident it is with its score. And so you could say if a certain prediction is high confidence or not by just setting a cutoff. And so from these high confidence scores, I measured the off by n error. So basically the number of jumps plus or minus that we were off from the human judges. And so the way to read this plot is we got about 20% of the videos perfectly accurate. And then about 75% of the video, about 75% of the videos, we were within 2 of the human judges. And then it just slowly increases up to 100% at around 8. So that's not great. It's not accurate enough, I think, for a competition setting yet, but I still think it's pretty remarkable that we can get within 2 on 75% of all of these videos. Just a few more demos. It works in other events as well as relay events. So I'll skip ahead to where the switch occurs, and you can see, whoops, go back a bit. So you should be able to see the prediction drop as the switch happens, but then it detects Zach's periodic motion and starts counting him instead. So you see it dropped right there, and now it picked up on Zach's periodic motion, and it's continued to count at his new double under rate. There's a mistake. It looks like it captured that as well, so pretty cool. And it also seems to work for double Dutch as well. I don't have a big data set of double Dutch videos, so I haven't really evaluated it that much. But here's a video of Noah doing some really speedy double Dutch, and it is pretty accurate, I think. I don't remember the actual true count for this video. I think it's within like 3 or so jumps. And interestingly, there's a lot of background periodic motion that would probably get in the way, but it still just picks up on this main periodic motion in the main frame of the video. So I do want to present a failure case of the model, and I would also like to congratulate Mason Meek on his unofficial 30-second speed world record of 124. So I think what's happening here is you can see Mason's feet are just crossing by each other every single jump. And so I'm pretty sure the model has only represented a single foot moving up and down. And so it's probably going back and forth between counting every single jump versus counting only 1 foot. And so this is an interesting failure case that we would definitely have to account for if we wanted to use this in any real competition setting. So as far as the future plans of this project, I used the pre-trained RepNet model completely out of the box as is, trained on all of those synthetic YouTube videos. And it works pretty well, but there's this concept in machine learning called transfer learning, where we can fine-tune a model on a smaller data set. And I think we already have the infrastructure available to produce that data set automatically. So we already have Chris Brown's really cool speed replay system that's being integrated into competitions. And so we have a very controlled video environment for lots of different speed events. And we could sync these with the timing tracks and then the final scores from the judges to automatically produce a huge data set of labeled videos that we could then fine tune this model to perform even better on. So that would take definitely some more work, but it would be really interesting to see if it could be feasibly done. So that's everything I had prepared. If anyone has any questions, I'm happy to answer them if there's time. If not, you can just send some in the chat and I'll try to get to you.
Thanks, Dylan. That was awesome. There's definitely time for questions for at least like 5 or 10 minutes, so I'll open it up. But thank you. That was really, really cool.
Yeah, you're welcome.
I have a question. I know this is less likely for bigger competitions, but let's say we were using this at a smaller competition. We had novice jumpers. You know, sometimes they make a mistake and they do 2 jumps within like 1 spin of the rope.
Right.
Can the computer account for that?
So I would say probably not. So it's only detecting periodic motion, and it detects that based on, let me go back to this. So it detects that based on basically this temporal self-similarity. So you could imagine it would have a bunch of frames of that novice jumper jumping correctly, jogging stepwise, but then in those few frames where they are jumping, but the rope's not actually going around, it would look very similar to their correct jumping. So it probably would count those. So yeah, that would definitely be a failure case that we would have to address. And also, I think that it wouldn't correctly account for mistakes in the way that we currently judge them, because it probably wouldn't, skip a jump or anything like that. But if it is 100% accurate, we could eliminate that sort of judging rule because it's only in existence because we know humans make mistakes. But yeah, thank you. Great question. I see there's a chat message. I don't know if it's a question. Let me open that up. Do I see any other applications for this outside of competition? Yeah, I think so. I think it could be useful just in practice. If you want, I don't know, some way to accurately count yourself in real time if you don't have someone there to count you. There's no sort of user-friendly application available for this right now. The only way you can use it is if you're a little bit familiar with code, but there is a free implementation available for this. So if you have any videos you want to test it on, you can just plug them into their model online if you know a little bit of code. But right now, yeah, there's not a good way to get this out just to everyday jumpers to get them to use it. But I do think there could be applications outside of competition.
Dylan, it captures the change in speed or like the rate, correct?
Right, yeah.
I'm curious. Okay, I'm wondering if like you think it could be used for something like 3-minute speed and like looking at videos of like people who are scoring the highest and where their speeds are slower versus faster. I'm thinking like in track, we always get trained for like a 400 to go like faster at certain times or around the bend. If that could be used to kind of like optimize speed scores or speed training for like longer events and stuff like that.
Yeah, that's definitely an application. Let me actually show really quickly one other thing that I didn't include in this presentation. So the model is not just for counting periodic motion, it's for analyzing all sorts of periodic motion. So the example they give shows specifically, speed change detection. So they have a really good example of that. So you can see mountain climbers slow and then fast, and you can analyze the full extent of that periodic motion, not just counting the number of periods. And so you could generate a curve like this for the entire 3-minute speed event, and you could see where they start off, where they speed up, where they slow down, and so on. So yeah, there's definitely other applications of this beyond just counting. Anything that involves analyzing the periodic motion of a speed event could be done.
Very cool.
Yeah, it's a really, really cool model. And I think there's more to it than just the applications. I think there's something inherent to counting repetitions, just like as far as perception goes. I think it's just something that intelligent beings can do.
I kind of have one question with like a tacked on follow-up question in terms of like how to actually potentially implement this at a competition and use it to score speed. So I imagine because it's like a program, you'd have to like collect videos and then run those videos through the program and then you get scores, right? And then so instead of getting like real time like scores from judges hand counting, I guess that's kind of like a time delay, right? But like, do you think like with this program, does it seem like something that could go fast enough to where it would actually save us time in the end? If that makes sense.
So I think it could be real time. I sort of left out a few details. It doesn't actually process the entire video. It only processes 64 frames at a time. And so if you have, say, 30 frames per second video, you could process all of those and give, a frame every 2 seconds, like an update every 2 seconds, which is not quite as real time as we currently have. But I mean, I think it would be enough for a 30-second event to have, 15 updates during the course of the event.
Gotcha.
But it is dependent on the hardware you have. So actually training the model is completely infeasible for anyone except for Google. So this is out of DeepMind, which is Google's big AI lab. And in the paper, they report the training time that it took to train the model, and they report it in GPU years. So they trained it on thousands of graphics cards. But if you were to train this on a single graphics card, like on my laptop, it would take like 50 years. But they did it in a
okay.
but fine tuning the model would not take that long. So that's usually what transfer learning is for, is you have this massive model built by Google or something, some crazy company that has access to these resources. You can't train that model from scratch, but you can fine tune it on your small data set, and that's feasible.
Gotcha. Thanks.
All right. Are there any more questions before I stop the recording?
Yeah, if you guys think of any questions, you can just send them in the chat, message me at any time. Just let me know.
Sweet. All right.